like say before a workout or just anytime?
So another fascinating question. So a lot of pre-workouts have creatine in them, and there are no acute effects of taking creatine. Um, everything. There's no acute effects. So you take some today, there's no benefit today. Ellis, you want to say hi? No. Okay.
I'm shy.
You're shy. You are absolutely not shy, my dear.
Yeah, yeah,
Okay.
yeah, yeah, yeah.
So you have to take a lot of creatine. You have to take it over usually a week to 2 weeks before you can get enough that it gets fully absorbed into your system and gets into your muscles and makes the muscle amount go up. So you take some today, right? Digestion, absorption, it's gonna take a couple of hours anyway for it to get into your system. And there's such a small amount that is in there that having it in your blood doesn't do you any good. It actually has to get into the muscle, then it has to get phosphorylated and things in that way. So there's usually this loading phase where you take a bunch for a couple of weeks, and then you can kind of dial back and take like a maintenance dose after all of that. So the timing is really not it's really not that tricky. It's just have some, and in a couple of weeks, if you're a responder, you'll have more. Now there is some evidence on kind of the amount you need to take. And it's oftentimes usually more than the amount that's in pre-workout and those things. I don't know, was that kind of what you were aiming for, Haley?
Yes, absolutely. Thank you.
Okay. So everybody gonna run out today now and go buy some creatine with everything. Okay. So those are great questions, guys. I appreciate that. Ty and I will try to pull a couple of figures and those sorts of things and show you guys a little bit more about kind of how we know what we know about creatine on Friday. Okay. Okay. Let me do share, and then we'll go here. All right. So we're going to talk about metabolism now. And as I said, this is the most conceptually difficult thing that we're going to do. And the reason that I think it's conceptually difficult is in some ways illustrated by what's happening on kind of my opening kind of title slide. And now you guys don't have to memorize all of this, although parts of what is on here you are going to have to know. But what this is showing in some ways is this is this is a summary of aerobic metabolism. This is a summary of what your body is doing all the time in the mitochondria in your muscles. And so what you can see in yellow is this is potentially, if we get into real distress, our ability to use proteins as fuel. You can also then see in the green that we're using carbohydrates, and then in the pink you can see that we're using fat or lipid tissue. And what you will note from all of this, right, is there's multiple carbohydrates here. There's glycogen, there's carbohydrates stored as glycogen in several places, but that all of these things are all sort of dumping stuff into this common acetyl-CoA step here, and then going into the Krebs cycle or the citric acid cycle, and then the electron transport chain. As you guys sit there right now, right, every one of you is maybe not using proteins, but you are for sure using carbohydrates and fat, and all of these things are running simultaneously and putting them into the Krebs cycle, and you're getting ATP out of it on the back end. And what you guys have probably learned before is that you do one thing, then you switch to another. Then when that's gone, you switch to fat or you use fat. And then when that's gone, you switch to carbohydrates. But there's this sort of everything happening at once idea. And this is just aerobic metabolism. There's also stuff happening in anaerobic metabolism all the time that involves different substrates and things. And so, and then how this works during exercise is going to depend on, are you sitting? Are you walking? Are you jogging? Are you jogging really fast? How well trained are you? Did you just eat some carbohydrates this morning? Did you eat some fat this morning? Right? What do your glycogen stores look like? So there's all of these different things that influence the extent to which each one of these kind of colored portions of the pathway are going to contribute to your overall sort of ATP that you are making. Okay. So we're going to start metabolism, and I'm going to say something now, and I'm going to keep coming back to it all the time. Okay. All the time. So please, please, please write this down because this is the big take home. Okay. Metabolism is about energy creation. Okay. It's about making ATP out of some substrate. Okay. And a substrate could be a sugar, right? Some kind of carbohydrate. It could be from fat or some sort of free fatty acid that's come from something you've eaten or from adipose tissue or something or from protein. The idea with metabolism is at all times, our body needs a certain amount of energy. If you're sitting, that amount of energy is less than if you're walking. If you're walking, that amount of energy is less than if you're jogging, and so on and so forth. Okay. Your brain needs energy. Your heart needs energy to contract. Your diaphragm needs energy to contract so that you can breathe. Okay. All of your cells are running processes right now as we sit here. You need a certain amount of ATP. And we have to have a way to make that ATP from somewhere. And in the majority of circumstances, the cells don't care where the ATP comes from. The cells just know we need X amount of ATP. Okay. And so what we're going to dig into is what are the things that happen that are going to cause cells to need more energy or less energy? And then how does that requirement of more or less energy alter sort of the pathway and the substrate that we're using to provide that amount of ATP? Then we're going to talk about what happens if you can't make that much ATP. What happens if the demand by your muscles in particular exceeds your ability to actually make that ATP. Okay. And that's going to be an instance when we get what's called fatigue, right? You are not going to be able to make enough ATP to be able to do things. Okay. So I'm going to start before we even jump into everything else. And so I apologize, some of y'all. Actually, for those of you that have your, what happened? For those of you guys that have your cameras on, you're gonna not have to answer. So I'm just gonna pick someone else as I go down here. Lexi, are you there?
Yes.
Okay, Lexi, here's my question for you. Okay, here's my question. Um, as you're sitting there, okay, where do you think you're getting most of your energy? Which metabolic pathway, or do you even remember a metabolic pathway?
Um, I am honestly not sure.
Okay. Would someone like to try to help Lexi? Who thinks you know what metabolic pathway is active right now? Anybody want to guess? No one? No one? Okay. That's fine. Sydney, are you there?
Yeah, I'm here.
What metabolic pathway do you think is active right now?
Okay, I don't want to embarrass myself, but is it like oxidative
Mhm.
phosphorylation?
Absolutely.
Okay,
Absolutely.
good.
Hey, and also, right, everybody, we're going to tell Sydney this is a safe place. This is a safe space, right? I know I'm probably not supposed to use those words as much anymore, but this is a safe place, right? We're all here. Um, we all know some things, we don't know other things. It's okay to be wrong here. It's okay to be wrong. So, oxidative phosphorylation. So, aerobic metabolism is active right now. That's right. Okay. Anybody else? Are there other pathways that are active right now? Okay. Um, on my other thing, Kate.
I was going to say oxidative phosphorylation too.
Okay. Um, this is great. I've got more than one Kate. Um, so Kate Oxfaz. Anybody else want to guess on a different one?
Glycolysis?
Glycolysis. Yes, that's right. Was that Nadia? Was that you that said that?
Yes, correct.
That's right. Glycolysis, right? So here's a fun question for you guys. Is glycolysis aerobic or anaerobic?
Can it technically be considered both?
That is
Like,
probably how you guys have been taught. Um, Technically, glycolysis is an anaerobic pathway. It does not use oxygen anywhere in the entire pathway. Now, the product of glycolysis, when you make pyruvate at the end of glycolysis, that pyruvate can either get turned into lactic acid or it can go into the Krebs cycle. So the products of glycolysis can be either aerobic or anaerobic. And so there's some ways to kind of move this stuff around. Okay. All right. Thank you guys. So everyone write this down. Everyone write this down because this is the other piece of this that I want you guys to know. Okay. And that is every metabolic pathway is active all the time. All the time. Okay. You have free ATP that's being used all the time. Almost all the time, I guess. You're using creatine phosphate as a substrate a lot of the time. You're doing glycolysis by itself where it makes lactic acid all the time. You're using oxidative phosphorylation all the time. Within that oxidative phosphorylation, you're probably getting energy from carbohydrate substrates all the time, fats all the time. Okay. And so all metabolic pathways are active all the time. What's going to happen is, based upon what you've eaten and what the ATP demand is, certain pathways are going to predominate at one point in time versus another. Okay. And that's the big thing that we're going to need to figure out as we're not just going to learn the pathway. We're going to learn, why is the pathway fast or slow? What happens as it speeds up or slows down? And how does that play into collectively how much energy are we getting from that particular pathway? Okay. So that's why this is conceptually difficult, because they're all active all the time. But the balance of where you're getting your energy from as you're sitting there listening to me talk versus if you were walking or if you were running fast or something is going to shift. And we've got to understand what are the things that are going to cause that shift. Okay. Okay. So a lot of the stuff that I've just talked about is kind of covered in this very first slide. Okay. Metabolism is unquestionably the process of deriving chemical energy from breaking down foodstuffs. So carbs, fat, protein. Okay. Why is metabolism important? Well, metabolism is the process of making energy. And so the big issue is, to move, to be alive, we need energy. Yeah, Ellis, you can pick pumpkin up. That's fine. So we may have a cat joining me here in just a moment on everything. Okay. And so the reason that we cover metabolism after we've covered muscles and cognition to contraction and all of this is, you guys remember the question that Ty and I asked you during the Jeopardy game is, doing cognition to contraction, we need energy to repolarize membranes to run the sodium potassium pump. We need energy at circa to pull calcium back into the sarcoplasmic reticulum, and we need energy to break actin and myosin apart using the myosin ATPase. Okay. And so movement requires energy in a lot of different places. And so remember that energy use and those things in cognition to contraction is related to force production. Okay. If I need more force, I need more cross bridges, which means I have to send more signals. There's more things to repolarize. There's more active fibers. So there's more calcium that needs to be resequestered. There's more cross bridges that need to be broken most of the time. So that means more energy. Okay. And so when you walk, you use a little bit of force. So you use a little bit more energy than at rest. When you run or you jog, you use way more force. So you need way more energy. Okay. That's why we do sort of the muscle side of things and the force side of things first. This is very much out of order for how the textbook presents things if you look at the chapters and things. But it makes sense to me that if you understand that we need the energy to generate force, then if we tie all of this back together with why is jogging more energetically sort of demanding than walking, and walking more than sitting, or walking uphill more than downhill, it all comes back to the cross bridges and the nervous system and how we're generating force. Okay. So the significance of metabolism with exercise, and I think this is really, really important, guys. And that's why we want to put at the start again, kind of big picture stuff. Okay. Many of our physiological responses that occur during exercise. So increases in respiration or increases in ventilation. So increases in breathing, increase in hormone release, okay? Changes in heart rate and stroke volume and cardiac output, sort of all of these other downstream things in our physiological systems occur as a direct result of changes in metabolism, because those particular systems help us support and regulate metabolism. If I need more ATP, I probably need to breathe more frequently and more deeply so I can bring in more oxygen to use to help me make more ATP. We'll talk a whole bunch about how we use hormones to regulate metabolism as well, how we use changes in the cardiovascular system to distribute blood to certain tissues to carry those carbs and fat and oxygen out to the muscles that are going to need them. Okay. So our responses are related to metabolic responses. Metabolism responses are related to force, and then, right, all these other things are related to metabolism, which is related to force. So in many ways, changes in breathing, changes in heart rate, all of this stuff comes back to changes in force production. Adaptations to training are often very much proportional to the energy demand during training, and a lot of this is specific to aerobic training. Excuse me, to aerobic type training. Okay. The more energy you use, the greater the stimulus there's going to be to drive changes in capillaries and mitochondria and things to help us provide more energy in the future. Performance, especially in very long distance events and in very high intensity events like sprinting or doing like reps to failure or something, is very often limited by the rate that energy can be made available. Okay. You guys can only sprint so fast for a finite amount of time. And after about 8 to 10 or 12 seconds, you're going to slow down. It doesn't matter if you're, you know, an Olympic 200-meter runner who can run really fast for, 19 seconds, or if it's the rest of us doing that and it takes us 30 seconds, we're still slowing down at about the same point. Okay. And that's limited by I cannot make enough ATP to continue that high level of force production. Or in very long distance events, it may be that I can't make enough energy to continue to supply energy to the brain and energy to my muscles for a host of really interesting reasons. Okay. And then fatigue, or you're having to slow down or limit force production, can be caused by decreased availability of energy or an accumulation of certain metabolic end products. If we run anaerobic metabolism at high rates for a very long period of time, and by long, I mean just a couple of minutes, you're going to make things that turn off the metabolic processes and will force you to stop exercising at that particular rate. It's all going to come back to metabolism. Okay. Okay. Anybody have questions about that up to this point? Are we okay so far? Right? Many of you all in your assessments said you really like the idea of kind of the big picture and tying things back together. And so I just want to see if we're getting there. Okay, there was a chat. Miles wants to know, can you mentally push past the point of fatigue? That's a great question, Miles. And so the question and the answer, or I guess the answer is, as with all questions in classes, it depends, right? It depends. There is a type of fatigue where you can make enough energy to continue, but your brain essentially says, shut it down. And in those instances, yes, you may have some ability to push through that, depending upon other circumstantial things. That's called central fatigue. There are other instances where no, like the sprinting example. If you're sprinting as fast as you can, right, after about 10 or 12 seconds, you just cannot make enough ATP to continue at that particular rate. You should still be pretty motivated for after those 10 or 12 seconds. You're still trying really hard. There's nothing that you can do. You're just going to slow down, right? Maybe if we were doing squats, right, I could have you guys do enough squats at some point, especially if it was pretty heavy. You just can't do another squat. You're trying, you want to do another squat, you're really motivated, but you just can't do it. And so in that instance, no, right? No, you can't. So it really depends. And we'll talk probably the very end of next week. We'll talk about the sites and locations of fatigue and the kind of intricacies of all of that. So a really good question. Okay. Okay. So let me do this back the way that it was. I don't really understand what I have done on all of this. Nope, I don't want to be here. Okay. All right. So some basics, right? For any of you guys that have had physics at all, or maybe y'all cover this in chemistry, I have forgotten. The idea behind energy is that energy is related to the ability to perform work, right? Because that ATP lets us generate force, lets us move. That's going to get us this idea of work, or force times distance. Okay. And this is a very strange concept. Energy emerges when a change takes place. And so it gets us into this idea of bioenergetics and the first law of thermodynamics. Okay. Bioenergetics is basically the flow or the exchange of energy within a living system. Okay. You guys have a bunch of energy substrates stored in your body. So you have this capacity to generate energy, but you got to do something to then essentially drive moving it from that storage site and put it into motion or into work in your muscles or someplace like that. So I like to talk about the first law of thermodynamics because I think it helps us to understand how our metabolic pathways work in the body. Okay. And so the first law of thermodynamics tells us that energy cannot be created or destroyed, but it transforms from one form to another without being depleted. Okay. And now we've gotten into philosophy class, and right. So like if it can't be created or destroyed, where did it come from? Right. All of these other sorts of things. But what I want you to take from this though, right, is that it cannot be created or destroyed, but it basically transforms from one to the other. This is what is happening in your metabolic processes. Okay. You have some stored energy in one place. And what you're going to do is take it from that storage site and actually pull it out and then use it. And then we're going to move it back around, and we're going to take our ADP and we're going to move it back around and kind of recreate it from someplace else. And so all of our metabolic pathways are in essence this sort of cycle, if you will, of do something, make ATP, pull the phosphate off, turn it into ADP, and then use our metabolic processes to put the phosphate back on. And so it's just this endless cycle of going from ATP to ADP, sometimes to AMP, but mostly to ADP, and then back, and pull it off and then go back, pull it off and then go back. So it's just this big circle. Okay. And now it's become the Lion King, and this is the circle of life. So, okay. So that's the idea of energy. ATP is our primary substrate, right? You have the big thing to take away from all of this, right, is that you have very, very little ATP in your cells. As you sit there right now, you have very little free ATP in any of your cells. Okay. Maybe 80 to 100 grams total in your body, but it's a very, very tiny amount. And so because of this, this is why we have to have metabolic pathways. Because you can't store much, it gets used up really quickly, converted into ADP. You're going to pull one of these phosphate groups off. So we have to use our metabolic pathways to turn that ADP back into ATP. Okay. If in another instance you were able to store a huge amount of ATP in your cells, we wouldn't need metabolic processes. You just use up your ATP and you've got plenty and you can do what you need to do. And then when you'd stop, maybe you'd eat some more and it would all come back or something. But that's not how we function. Your cells are only so big and you just can't put that much in there. Okay. So the big thing that we're going to go through with metabolism is I don't have very much. So in any moment in time, I may need to use several pathways and several substrates, carbs, fat, protein, okay, to make more ATP. I've used up what is in my cell. Now I need to make more right now, okay, so that I can continue walking or running or biking or whatever it is that you're doing. Okay. Your brain always needs ATP, so you've got to be able to resynthesize something like that too. Okay. We're going to get into what are the pathways, what are the substrates. Okay. We're going to spend an inordinate amount of time going through some of those. And I will tell you guys, right, that while they're all being used all the time, the pathway and substrate that is the primary source of energy at any moment in time is going to vary based upon the mode of exercise. It really varies based upon the intensity of exercise. Okay. The presence or lack of oxygen, which most of the time we've got plenty of oxygen. How well trained you are, right, which controls how many mitochondria you have in your cells. Maybe some portions of fiber type is going to play a role. Okay. And then your diet. What have you eaten recently? If you've eaten a bunch of carbs, you're going to use a lot of carbohydrates. If you've eaten a lot of fat, you're going to use a lot of fat. Okay. So there's going to be some things that go into all of that as well. Okay. I'm just checking my time here. So what we've got then is the various substrates. So carbohydrate is going to be one. We're going to use glucose as our kind of carbohydrate surrogate. Okay. You're going to use the same relative pathways and things to metabolize other forms of carbohydrate, right? Glucose, maybe fructose, sucrose, galactose, maltodextrin, any kind of carbohydrate. And a lot of what happens is they just get converted back into glucose. Okay. We store carbohydrates as glycogen, and you have glycogen that's stored in your liver and glycogen that's in your muscles. Okay. And so the storage site is going to depend where that glucose that comes out of those storage sites is going to be used for slightly different purposes. So we'll cover a little bit of that probably on Friday. Okay. You have fat or lipids, okay, that are going to be stored in adipose tissue. You've got some stored fat in your muscles. You also have some fat in your liver. Although to be honest, if you got too much fat in your liver, you're likely going to become a type 2 diabetic. You have floating around in your blood, you have things called free fatty acids. They're usually bound to albumin or some other sort of carrier molecules. You also have cholesterol bound in your blood. And you may have things like glycerol and stuff in there as well. Okay. We store way more energy in your body as fat than we do as carbohydrate. Even in the person with the least amount of body fat that you could ever think of, they're still storing days and days worth of energy as fat in your body. Whereas in carbs, depending upon what your blood glucose levels is, you only have enough glycogen for maybe a day's worth of ATP or something like that. The last substrate is protein, which we can break down into amino acids. We can convert those amino acids in the liver into glucose through a process called gluconeogenesis that I will show you guys. Or in some instances, we can go through the urea cycle and we can stick the amino acids directly into the Krebs cycle. Okay. We typically only use protein as an energy substrate if you are in a negative energy balance. Okay. So let's just say you're on a caloric restriction diet, let's just say, then you may start to break down muscle tissue and try to use those amino acids from your muscles to make energy. That's a thing that can happen. And so for the most part, we try to not use the protein whenever possible. That's our last sort of resort with everything. Okay. Here we're going to have a bunch of words that look and sound the same, but they are kind of important as they relate to different metabolic processes, but they're gonna mean slightly different things. So I want you guys to follow me as we walk our way through all of this, okay? The first word is glycolysis, okay? Glycolysis. The glyco meaning carbs, or really the glyco means glucose, which is a very strange kind of thing that you would think that it should be glucolysis, but it's not. It's glycolysis. This represents the breakdown of glucose into ATP and a substrate called lactic acid, okay? We'll talk a whole bunch about lactic acid on Friday. That's glycolysis. This is a metabolic pathway. This is a breakdown. You have glycogenesis, right? The genesis meaning to make or to put together. So the glyco here means glycogen. Otherwise, in glycolysis, it actually means glucose. But here, it means to make glycogen. So you do glycogenesis when you eat extra glucose. You are going to make glycogen in your muscles and make glycogen in your liver out of those extra glucose molecules. Okay? Lysis to break down, genesis to make. We then have a process called glycogenolysis, which you may think, well, that seems like a weird word, Dr. Black. It has the sort of start of genesis in there and also lysis. So are we making it and breaking it down? Actually, no. Glycogenolysis describes how we turn glycogen back into glucose. Okay. If I ask you to start doing squats right now, you are immediately going to start the process of glycogenolysis in the glycogen stored in your quad muscles and in your glutes, okay, to make that glucose available to go into glycolysis. We will talk about a very key enzyme that drives this breakdown process, and that enzyme is called phosphorylase. We'll go through some stuff on Friday, and next Monday, there's going to be a few enzymes in the biochemical pathways that I want you guys to know, and so we will talk about those. Okay. The last pathway here, the last process here, is one of my favorite words in sort of all of biochemistry. I think it's a fun one to say, and it is called gluconeogenesis. So it's got the genesis, so we're making something. It's got the gluco, which you would think would denote glucose, and then the neo portion, which I honestly don't know exactly what they mean by all of that, okay? But what gluconeogenesis is making glucose from non-glucose precursors. This is happening in your liver right now as we speak. It's especially common to use if you have extra amino acids, say from protein that you've eaten in a meal or something like that. Is you take those amino acids and you make them into glucose in the liver. That glucose then goes into your blood, and then it can go into your muscles and get used in glycolysis. Okay, so we've got glycolysis, glucose into lactic acid. That's a metabolic pathway. Glycogenesis, which is making glycogen. Glycogenolysis, which is breaking glycogen back down, back into glucose. And then gluconeogenesis, which we're going to make glucose again from a non-glucose precursor. Okay. These are all going to have something to do with carbohydrate metabolism and how we're going to, you eat extra carbs, you make the glycogen. Okay. So that then when you need them when you're doing something, you can take those carbs and break them down as glycolysis. Or you eat extra protein or something and you make more glucose from there. So you can then use that glucose to get energy. So this is these different sort of pathways where we make things or break things down as we're going to shift, right, what is happening from a glucose perspective. So we can use that glucose to make energy. Okay. These are some old data, and I should probably look for a better updated thing. But this is a 143-pound person with 12% body fat, which would be a sort of very relatively small and slight gentleman. Okay. Or a kind of normal-ish sized but very lean female. Women do not generally have 12% body fat. The most lean women you guys can ever really think of are usually going to be in the very high teens in that way. But that person would have about 1,500 kcals or 1,500 calories stored as carbohydrates in their body. So at that particular person, maybe a little bit more than a day's worth of stored energy and carbohydrates. And then in that person with that amount, that relatively small amount of body fat, they've got about 72,000 stored kcals in fat. Okay. And so this is conceivably enough energy in fat, right, that you could break all of that down, that you could, if that person needs maybe 1,200 or 1,300 kcals per day at resting metabolic rate, right, they've got months of stored energy as fat. Okay. And so this is just to illustrate that you've got a huge amount of potential to use energy by breaking down fat. The problem is it takes us a while to actually get that fat broken down and then to get it to a place where we can use it. The carbohydrate can go much, much faster. Okay. Okay. I'm going to mention these things and then we're probably going to need to stop for today. We're going to break our energy pathways down into three very broad categories. Okay, three broad categories. We're going to have what we call the immediate energy pathways. So these are things that if you need energy right now, right, you need to get up and walk to the refrigerator right now. This is where the vast majority of that extra ATP is going to come from. It's going to come from what we call the phosphagen systems. And that is stored ATP that's inside your muscles, okay? A energy substrate called creatine phosphate, which I'm sure most of you guys have heard about, okay? And then there's a reaction where we're going to take two ADP molecules and make AMP and ATP in it. So it's called the myokinase reaction. Okay. And I apologize for where the little bullet points are here, but these immediate phosphagen pathways, every one of these is anaerobic, so it does not use oxygen anywhere in the system, and they all occur in the cytoplasm of a muscle cell. Okay? They're all occurring in the cytoplasm of a muscle cell. These are important things to remember. Okay? You have ATP in the cytoplasm, it can get broken down immediately. You have creatine phosphate in the cytoplasm, it can get broken down immediately. And you have the myokinase reaction where you jam two ADPs together with the myokinase enzyme. That also occurs in the cytoplasm. And we'll go through the breakdown of each of these on Friday. Then we have this other anaerobic pathway that also occurs in the cytoplasm. We call these non-oxidative. They're sometimes called glycolytic, but basically what it is the process that's called glycolysis, okay? And that is the process of taking a glucose molecule and making pyruvate, and in this instance, having that pyruvate go all the way to lactic acid. That pathway does not use oxygen. Every bit of that pathway occurs in the cytoplasm. This pathway here makes about 2 to 3 times as much energy as we get from here. So it's better in that way. It's better. You're going to get double or triple the ATP. And then the last set of pathways are our oxidative or aerobic pathways, and they occur in the mitochondria. They need either the pyruvate that has come here from glycolysis, or they need basically carbohydrates coming from fat to be put into the mitochondria, go into the Krebs cycle, and then go down the electron transport chain and make ATP. Okay. Yes, Ellis?
When is the meeting gonna be over?
It is over right now, my dear.
For life?
Yep. Okay, guys, that's what I've got for today.
Yay!
Ellis is very happy that I am done talking to you all.
Yeah!
Oh, sweetie, careful, careful, careful. That is not okay. All right, that's what we've got. Be on the lookout for your grades. Be on the lookout for a worksheet from Ty and I will see you guys on Friday. I'm hopeful that we'll be on campus on Friday, but we'll see. Someone asked when I can get the YouTube videos uploaded. Those are the next thing on my list of things to do. I will get those up today, you guys. I promise. Okay. Any other questions? Nope. All right. You guys stay warm, okay? We'll talk to you soon.
Thank you.